Today, we discuss multiple missions that have been around longer than I have.
One has even been around longer than I have.
Really? I didn't know that was a thing. Anyway, we have spacecraft, and for those of you who wanted to escape, I have a review of the alternate timeline show For All Mankind.
I was born after Apollo. I'm not that old.
And we have planetary science, stellar images, and more.
All of this and more right here on the Daily Space. I am your host, Dr. Pamela Gay, and I'm not that old.
Really. And I'm your host, Eric Mattis.
And we're here to put science, old and new, in your brain.
NASA's Voyager probes have been coasting in interstellar space after leaving the solar system in the mid-2010s. A recent article in Scientific American said that the spacecraft would be shut down soon. That wasn't wrong, but a little misleading. The spacecraft have a few years left yet. NASA posted an update on the spacecraft Twitter recently saying that the spacecraft were still functioning, and will continue functioning up until the 2030s if possible. 5 of the original 11 science instruments are still running, and NASA expects they can continue operating these instruments until 2027. After that, Voyager will just phone home, sending and receiving data. Its transmitter only uses 23 watts of power, 2.5 times less power than the average light bulb. And that tiny amount of power sent us back thousands and thousands of amazing pictures and scientific data on Jupiter, Saturn, Uranus, and Neptune. The Voyager spacecraft are extremely simple, very little software to go wrong. The whole spacecraft has less memory than a key fob, according to Linda Spilker, a JPL scientist quoted in the Scientific American article. Microprocessors weren't around when the spacecraft was being designed. Most of the vehicle functions are hardwired. The one resource driving how long Voyager can last is its power supply. Voyager uses radioisotope thermoelectric generators, RTGs, which take the heat produced by small pellets of plutonium-238 and convert that into a trickle of electricity. These were chosen because the spacecraft will be operating in the outer solar system and beyond, so solar panels will be insufficient. RTGs can provide power for decades, but Voyager has been in space for 45 years, so the mission will be coming to end in a few years, just not right now. From a spacecraft that keeps trucking on, we go to some great news about a spacecraft still in its prime, and it involved pretty rocks, or at least pretty craters.
Space exploration is slow. It takes time to build missions. It takes time to fly missions to their destinations. It takes even more time to transform images into a new scientific understanding. My favorite example of the slow march of science is the BepiColombo mission to Mercury. On June 23rd, this mission made its second flyby of its target, sending back stunning images of this poorly understood world. In 2025, BepiColombo will enter orbit around Mercury in 2 parts: ESA's Mercury Planetary Orbiter and JAXA's Mercury Planispheric Orbiter. Together, these twin spacecraft will study Mercury in gravity, magnetism, light, and chemistry, allowing us to understand how it is shaped from the inside out. For now, the mission is just going to fly by as it uses Mercury's gravity to adjust its orbit. This is flyby 2 of 6 that BepiColombo will make of Mercury. It has also made 1 flyby of Earth and will make 2 of Venus. This mission was initially thought through in the 80s and 90s. It was named in 1999. It will arrive at its target in 2025. This is multi-generational science like Voyager, where the people who design the mission know it is the students of their day who will someday do the eventual science of tomorrow. Some science requires generational amounts of time, and some science requires eons worth of time. Such is the case with the scientists trying to understand an event known as the Paleocene-Eocene thermal maximum, or PETM, which occurred about 56 million years ago. During this time, the planet warmed by 5 to 8 degrees Celsius, resulting in the extinction of numerous deep-sea organisms. Now, in a new paper to be published in Nature Geoscience, scientists analyzed cores taken from the North Atlantic and found substantial evidence that the final stages of Greenland and Europe rifting apart released massive amounts of carbon from the mantle. The evidence shows that this period of intense volcanic activity lasted over 200,000 years, which makes it a close match to the 170,000 years of the PETM. Lead author Tom Gurnon explains, quote, "This finding is significant because we know the parts of the continental mantle in this region are enriched in carbonates, a major source of carbon. This rapid increase in mantle melting likely released a very large volume of carbon, certainly more than we had previously expected." End quote. Because the PETM resulted in a distinct global warming event, scientists are using it as an analog for the current climate change, despite the difference in mechanism. They're interested in the cause, but they are also interested in the biological outcome. A mass extinction event changes the course of evolution on Earth, and that seems to be where we are currently headed. Okay, that story requires a bit of a palate cleanser. For those of you watching us on Now Media or on YouTube, I now present the globular cluster Terzon 9. If you're listening to the podcast, you're just going to need to click over to dailyspace.org to check this picture out. The good folks at the Space Telescope Science Institute have released a stunning image of the globular cluster Terzon 9. Located toward the bulge of our galaxy, this bedazzled system is part of a research study of globular clusters located in high-density regions. Normally, these puffballs of stars linger in the outskirts of galaxies. It's not understood how they form, but this research may help us understand how the systems can be affected by their environment. That research, well, science takes time. For now, we just have a reminder that the universe wears some truly beautiful gems of light. And now, let's look down, not on Earth, but on Europa, as we think about the worlds we can dream of the next generation exploring. Stay tuned. I always find it amusing and interesting how, in the lead up to a planetary mission launch, scientists start using every possible space and ground telescope to stare at the future target ahead of the mission's arrival. We saw this with New Horizons, where the Hubble Space Telescope helped discover 2 more moons at Pluto as the team was looking for potential spacecraft hazards. And now, as we get closer to the planned launch date for Europa Clipper in 2024, Hubble is at it again. Using ultraviolet observations taken by Hubble, a team of scientists has mapped out the sulfur residue on the surface of Europa. Okay, that sounds like a somewhat weird thing to map out on a planet with an icy surface and a potentially massive subsurface ocean, but bear with me here. All of that sulfur on the surface could help us understand the composition of the ocean. And in that ocean rests some of our best hopes for finding life beyond Earth. Not unexpectedly, the new ultraviolet map for sulfur dioxide correlates with images taken in visible wavelengths that show dark surface regions. What's even more interesting is that the sulfur is mostly concentrated on Europa's trailing side. Co-author Philippa Molyneux explains most of the sulfur dioxide is seen on the trailing hemisphere of Europa. It's likely concentrated there because Jupiter's co-rotating magnetic field traps sulfur particles spewing from Io's volcanoes and slams them against the backside of Europa. End quote. That magnetic field then causes a chemical reaction between the water that reaches the surface on Europa and the sulfur that arrives from Io, creating the sulfur dioxide residue. On a side note, this paper also confirmed that the suspected water ice on Europa does not, well, look like water ice in the ultraviolet. The team will continue to investigate this discrepancy, but an answer may have to wait until Europa Clipper reaches the Jovian system and sends back data. One mission that we don't have to wait for is NASA's Juno. That amazing spacecraft has been doing close flybys of Jupiter since 2016, analyzing the magnetic fields, the atmosphere, and even the moons. Now, in a new paper published in Astronomy and Astrophysics, scientists have determined that Jupiter's atmosphere isn't a homogeneous mix of gases and actually contains a significant amount of metals. And by metals, we mean elements that aren't hydrogen and helium, because that's how astronomers roll. Okay, we have a confession to make. The press release for this story came out early in June, but didn't cross our radar until yesterday when a trending article on Twitter had the title, "Bizarre News Story of the Day, Jupiter Apparently Eats Other Planets." That got our attention, and so we found the paper and the press release. In the interest of journalistic integrity, no, Jupiter does not eat other planets. Not now, anyway, and really not on purpose in the past. It's not hanging out there in the solar system, pulling in large worlds and demolishing them. But back in the planetary formation period of our solar system, Jupiter did have a tendency to pull in kilometer-sized planetesimals. To find this out, the team analyzed gravitational data collected by Juno, which allowed the team to see below the stormy surface to the inner envelope of the planet's atmosphere. They found more metals in the inner parts of Jupiter's atmosphere than in the outer layers. Lead author Yamala Magal explains, quote, "There are two mechanisms for a gas giant like Jupiter to acquire metals during its formation: through the accretion of small pebbles or large planetesimals. We know that once a baby planet is big enough, it starts pushing out pebbles. The richness of metals inside Jupiter that we see now is impossible to achieve before that. So we can conclude the scenario with only pebbles as solids during Jupiter's formation. Planetesimals are too big to be blocked, so they must have played a role." End quote. The findings in this research mean that Jupiter doesn't have convection below the surface as previously thought. And it also doesn't mean that Jupiter eats planets, despite headlines that say otherwise. But hey, the headline caught our attention. And now you know the science behind the story. Coming up next, Eric is going to review the latest season of For All Mankind. Stay tuned.
Before we get to the review of For All Mankind, a very near future, currently scheduled for next week, mission to explore the moon. Rocket Lab will launch one of their company's Electron rockets carrying NASA's CAPSTONE, or Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment, to near rectilinear halo orbit of the moon. This will be Electron's first mission beyond Earth's orbit. Electron will yeet the 24-kilogram, big for CubeSat, small for RealSat, payload to its special lunar orbit using a brand new cake stage, the Lunar Photon. It is much bigger than the regular cake stage, and on future missions will take Rocket Lab payloads to other planets. CAPSTONE will take months to get to lunar orbit after delivery to its trajectory by Electron and Lunar Photon. This is because it uses a ballistic capture method, a trajectory that saves a lot of propellant, letting it launch on smaller and cheaper rockets at the expense of time. The ballistic capture method uses the moon and sun's gravity to pull the spacecraft closer to the moon, so that the spacecraft only has to use a little fuel to insert itself into orbit. NASA's Orion spacecraft isn't going to be using the near rectilinear halo orbit anytime soon. CAPSTONE has plenty of time. Once in this special orbit, CAPSTONE will first check that the orbit is good for future spacecraft, and that a spacecraft can leave and return to it. It will also demonstrate, quote, spacecraft-to-spacecraft navigation services that allow future spacecraft to determine their location relative to the Moon without relying exclusively on tracking from Earth. It will also demonstrate a small atomic clock, also used for navigation. Instead of a camera or lens review this week, I'm reviewing a TV show, For All Mankind on Apple TV+. Season 3 is now out, and this will be a review of the first episode entitled Polaris. If you haven't watched the first 2 seasons, you should hit pause, binge watch them, and then come back and unpause. For All Mankind is Apple's alternate history of the space race. For those who haven't seen it yet, the basic premise is, what if the space race continued? Season 1 concludes with a permanent US lunar base. Season 2 ups the tension, and global nuclear war is averted at the last moment of the season's finale, but not before a dramatic and ultimately pointless major character death and a dogfight between 2 space shuttles in lunar orbit. Yes, space shuttles, plural, in lunar orbit. How they got there is never really explained in the show directly. Season 3 takes place in 1992, 10 years after the end of Season 2. Like the beginning of Season 1 and 2, there is a montage of historical events that further branch off from our timeline to bridge the seasons. One event that differs is the launch of the WST. Instead of having that name and launching in 2022, it is launched in the 90s and is named after Thomas Paine, a real-life NASA administrator who, in universe, dies on Cal 007. The Paine telescope was also designed to be repaired in orbit. A mention of this happening occurs in the episode proper. However, the major focus of this season is the first human landing on Mars, which was hinted at in the Season 2 finale and Season 3 trailer. A secondary plotline in Season 3 is the introduction of commercial space tourism. The first episode features a visit to the Polaris Orbital Hotel, which is attached to what looks like an ISS, built during the 10 years between Seasons 2 and 3. Several of the main characters from the last season are in the hotel before it opens for their kid's wedding. An accident happens at the station that almost results in a massive structural failure, but it's averted at the last moment, of course. But not before a couple of station workers are violently killed, though. Writing-wise, the season opener was okay, but I found the station crew's dialogue during the emergency a little stilted and bland. In general, the technical discussions the characters have don't feel very organic, just randomly listing concepts and components, like they're talking about, oh, the blah blah jig, that will fix the problem with the engineinator, when they're talking about a niobium nozzle on a nuclear thermal rocket engine, both of which are authentic pieces of technology. That's probably my rocket nerd brain, though. What really bugged me about the episode was the bringing back of one of the squicky subplots from Season 2 that was, in my opinion, just unnecessary. It did nothing to advance the plot, and a whole bunch of other fans didn't like it last season, or the reminder this episode. One of the characters in that subplot got to be a hero during the accident, though, somewhat redeeming him in my eyes. Though how he got the skills to pull this off is never really explained, except for a passing reference in the news montage to him becoming an astronaut. Despite all of this, I'm gonna stick to and watch the rest of Season 3 of For All Mankind, which is available on Apple TV+. This has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.